some examples last week of how we can use hash functions for providing authentication. Now, when I say authentication, in fact, we're doing two forms of authenticating. We're authenticating the user, checking the data came from the right user, and we're also sometimes authenticating the data, making sure the data that's received is the same as what was sent, which we also call data integrity. So in fact, the techniques we're looking at usually provide user or source authentication as well as data integrity. And we finished mentioning some properties that we need for the security of hash functions. In fact, we'll see later there's a table that shows that depending on where we use hash functions, they don't always require all these properties. So there are three main properties for security. The one-way property, also called pre-image resistance, weak collision resistance or second pre-image resistance. That is the first two. It's a bit confusing, the names. We'll see that breaking the one-way property and weak collision resistance, you use the same techniques, so there's similarities there. So you see second pre-image resistant and second pre-image resistant. They're very similar. And strong collision resistance, or simply called collision resistant, is the third property. So let's try and make those three properties clear and understand which ones are hard for the attacker to break, to defeat. So if a hash function has these properties, what does the attacker need to do to defeat the security of that hash function? Just in summary, we said one-way property is that with a hash function, if we can calculate the hash of some message, it should be difficult to go backwards, the inverse operation. And given the hash value, it should be difficult to find that message. That's the one-way property. Difficult, computationally infeasible. That is, with large enough values, particularly the hash length, it will take too long, no matter what compute resources you have. The weak collision resistant or second pre-image resistant property is that if we have some message X and we know the hash value of it, the hash of X, it should be hard for an attacker to be able to find some other message, Y, which has the same hash value as the hash of X. So given X, the challenge for the attacker is to find another message Y which has the same hash value. That is, H of Y equals H of X. Of course, we cannot use the same messages. They have to be different messages. So we'd say a hash function has this property if it is computationally infeasible for an attacker to do this, to find this other message. And the third property, collision resistant or strong collision resistant, it's similar to the previous one. It should be difficult for the attacker to be able to choose any pair of messages, X and Y, which have the same hash value. So the attacker, they get to choose of any two messages that they like, X and Y, and it should be hard to find any two messages that produce the same hash value. Whereas in the weak collision resistance, that's a different condition, and that the condition on the attacker is that given some message X, find another message with the same hash value. Which one is easier for the attacker to attack? Or in other words, which one is harder to provide in hash functions? The second one, strong collision resistance. And although the mathematics is not the same, the concept I will try and explain using a different problem which has similar characteristics, which is called the birthday paradox. And you don't need to understand the details or the calculations of this birthday paradox, but let's spend 5 or 10 minutes explaining it to demonstrate these.
Why is one-to-one mapping not a requirement?
Why is one-to-one mapping not a requirement? What do you mean one-to-one?
One-to-one mapping of the hash components when with the
1 to 1.
Hash,
So your question is about a one-to-one mapping given a message, M, take the hash of that and we get, let's say, lowercase h. What do you want? A one-to-one mapping from...
so meaning that h of m1 should give h1. That is one-to-one mapping. It would never be the same. Why?
Well,
Why is that not required?
in fact, we have two different requirements which are somewhat conflicting. First, note that our practical requirements are that the input can be variable size and the output is normally fixed and typically small. That is, the length of the hash value is fixed. For a given hash function, we always get the same length hash value. But normally we'd like to take any size input. I finished with a demonstration last week showing I can take a hash, calculate the hash of a file. So, if the hash is, say, a length of 128 bits, and the message is longer, the message length can be larger than 128 bits, then of course we're going to have multiple messages mapped to the one hash value. So we will not have a one-to-one mapping there. Because if the message, for example, is 1,000 bits in length, larger than the hash value, then there's 2 to the power of 1,000 possible messages and 2 to the power of 128 possible hash values. So multiple messages must map to the same hash value.
Does it mean that the bigger the size of the message, the weaker the collision resistance?
So this says that there'll be a many-to-one mapping here, but that goes against our properties, or makes it difficult for our properties, because we would like a one-to-one mapping, but we cannot have a one-to-one mapping. It means that it still must be difficult to find a mapping that goes to the same hash value, to find this collision. So even though there will be collisions, some messages will map to the same hash value. The security of the hash algorithm depends upon how difficult it is to find a collision. In theory, there are collisions, but how much effort does it take to find a collision? And that's what these properties are about. When we say computationally infeasible, we know it's possible in theory, but it should take a lot of effort, a lot of computation to find it. And we'll see when we get to the end of here, the security doesn't depend upon the message length, it in fact depends upon the hash length. The longer the hash, the more effort required to find a collision. So we don't have a one-to-one mapping. We would like one, but in practice we cannot. Now, let's try something completely different. How many people do we have here? Not a full class for sure. Of the 20 or so people, so we've got about 20 people in the room, what's the chance that one of you have the same birthday as me? Not the birth year, that's a low chance, but the same date, day and month. Just consider days a month. Well, how would we calculate it? So assuming everyone has an equal distribution or a uniform distribution of birthdays, that ignore twins and so on, so the day that you're born on, it can be from between 1 and 365. There are 365 days to choose from. Forget about leap years. So a question is, what's the chance that one of you have the same birthday as me or as another person? Well, how would you calculate that? Well, consider what's the chance, so of the 20 here, what's the chance of one person having the same birthday as me? Well, let's say my birthday is on the 1st of January. It's not. Then the other person, their birthday can be on one of 365 days. Okay? And the equal chance to be on any of those days. So the chance of them having the same birthday, well, the way to think about it is the chance that they don't have the same birthday. The probability that someone doesn't have the same birthday as the 1st of January is what? So the probability they don't have the same birthday, there's 364 days which they won't have the same birthday out of 365. Okay? So the probability that someone doesn't have the same birthday as me, or as the 1st of January, is 364 out of 365. And the probability that they do is 1 minus that, which is 1 minus 364 over 365. That's the probability that one person, if choose from just one other person, that we don't, or this is the probability that we do have the same birthday, which is 1 over 365. Now, there are more than one person in the group, there are 20 of you, so you can expand that. What's the chance that of 2 people, neither of you have the same birthday as me? Well, similar approach. What is it? It's the chance that one person doesn't have the same birthday, and the chance that also the second person doesn't have the same birthday as me or the same birthday as that other person. Okay, so of 3 people in the group, me and 2 others, what's the chance that the first one doesn't have the same birthday as me and then the second one as well?
364 over 365 multiplied 363 over 365. Remaining.
Okay, and now expand it to 20 people.
So it goes until 20.
And without wasting time on writing it down, I have an equation. In fact, we end up as here. So the chance that one person doesn't have the same birthday as me is 364 over 365, and the chance that a second person is also 364 over 365. So it's 364 over 365 multiplied by 364 times 365. So with n people, the probability that no one has the same birthday as me is 364 over 365 to the power of n. Okay. And hence the probability that someone does have the same birthday, this is that they don't, is 1 minus that. So this is, given some birthday x, what's the chance that of a group of n people that one of them has the same birthday as me? All right, we'll see the significance of this value or this equation shortly. It's described there with a more detailed example. Where's my pointer? So going back, if there are 2 people in the group, just considering 2 people, quite simple. I've got a birthday on the 1st of January. Probability that the other one does not have the same birthday is 364 over 365. If there were 3 people in the group, if I've got a birthday on the 1st of January, the probability that one of them doesn't, or person A does not have the same birthday is 364 over 365, and the probability that B does not have the same birthday as me is also 364 over 365. Hence, the probability that neither do, A nor B does, is multiplication of those 2 probabilities. And you expand that, that's for 2 people, that's 364 over 365 squared, and with n people, it's to the power of n. the probability that no one has the same birthday as X, and the probability that therefore that someone does is 1 minus that. Now, a different problem. Of the 20 people in the room, what's the chance that 2 people have the same birthday? Probability that any 2 people have the same birthday. Do you think it's greater than the previous case? So, if n is 20, for example, 20 people, what's the chance that someone has the same birthday as me? Would calculate 1 minus 364 over 365 to the power of 20, the 20 people in the group. We get some number. What if we ask a different question? What's the chance that any 2 people in the room have the same birthday? Do you think the probability will be higher or lower? It will not be the same. What's the chance that of this group of 20 people that 2 of us have the same birthday? Is it higher or lower than the previous one? Is the probability higher or lower than this? Let's try. Let's vote. Hands up for higher. Hands up for lower. Anyone? Hands up for don't know. Let's see. And the mathematics is harder, but so we will not try to demonstrate on the board, but let's just see. We use the same approach. So now the probability that any 2 people have the same birthday, it's 1 minus the probability that no 2 people have the same birthday. Okay? So if you take a pair of people, a pair, and the chance that they don't have the same birthday, and we do that in all cases, then it's 1 minus that. So now, what's the probability that no 2 people have the same birthday? First, consider a group of just 2 people. If one of them has a birthday on the 1st of January, then the probability that the other person does not have a birthday on that same day is 364 over 365. Okay? That's the same as before. What if we had 3 people in the group? Well, if one of them has a birthday on the 1st of January, probability that one of the other ones, user A, does not have the same birthday is still 364 over 365. And the probability that B, the third person, does not have the same birthday as the first one or the second one is 363 over 365. That is, I have a birthday on the 1st of January. The first person, the chance that they don't have the same birthday as the 1st of January is 364 over 365. There are 364 other days. And then the third person, the chance that they don't have the same birthday as me and that other person is 363 out of 365, because I have the birthday on the 1st of January. The other person, if they have a birthday on the 2nd of April, then the chance of a third one does not have a matching birthday. There are 363 days left. So for that second person, the chance is 363 over 365. And if we expand that group now, that was n equal to 2, n equal to 3, n equal to 4, we'll see the pattern. It's 364 over 365 multiplied by 363 multiplied by 362 and so on. And in general, we can expand that out and simplify, and it becomes some factorial. 365 factorial over 365 to the power of n times 365 minus n factorial. That's the probability that no 2 people have the same birthday. So here it's slightly different, or it's different in that The third person cannot have the same birthday as me or the other person. And that's why we got that case of 363 over 365. And then the probability that any two people have the same birthday is 1 minus what we just calculated. Now, to make sense of those equations, here's a plot where of those two equations with different values of n down the bottom. The red line is the first one. Given the way to read this plot is if there are 20 people in the group, okay, a group of 20 people, n equals 20, then the probability that someone has the same birthday as me is here. What's that? About 0.05, about 5% chance that someone has the same birthday as me. The blue one is the second case, the probability that any two people have the same birthday. So we take the 20 people here. What's the chance that a pair of people have the same birthday? It's getting close to 40% chance, much higher. Okay? That is, the chance that two of you have the same birthday is much higher than the chance that someone has the same birthday as me. We've got more degrees of freedom we can choose in that case. So the red one is the first case and the blue line is the second case. And we see that the probability of any two people having the same birthday is much higher than someone has the same birthday as an existing person. Why are we talking about birthdays? Similar concepts to the weak and strong collision resistance. Remember, weak collision resistance is the chance that the attacker can find another message with the same hash value as a given message. That's like the first case, like the red one here. The probability of doing that for finding a collision, here we're finding collisions of birthdays, two birthdays on the same day. With hash attacks against hash functions, we're trying to find collisions of hash values. The probability of finding a collision given some message, find another hash value, is not the same as, but think about the red line. Whereas strong collision resistance is the attacker can choose any two messages, find a collision. We can have any two people's birthdays, find a collision. The probability of that is much higher. The chance of an attacker finding a collision with weak, or if they're given some message, that is weak collision resistance property, is much lower than the chance that they'll find a collision if they can choose any two messages. So, which one is more secure? Or maybe easier. Which of the two properties, strong or weak collision resistance, is it easier for the attacker to break? Strong collision resistance. There's a higher probability that they'll find a collision, the blue one. Given the same size n, there's a higher chance that they can find a collision if they'll be able to choose from any two messages. So we say strong collision resistance, it is easier for the attacker to break that. Or another way to look at it, it's harder to provide that property. It's harder to make sure that it's impossible, practically impossible for the attacker to find a collision that satisfies that property. It's easier to provide the weak collision resistance property. The mathematics is not identical, but the concepts are the same as the birthday problem, the birthday paradox. That it's much higher chance that any two people have the same birthday than that one person has the same birthday as some given person. So coming back to here. some hash functions may have the weak collision resistance property. That means it's practically impossible for the attacker to find another message with the same hash value. But they may not have the strong collision resistance property. Even though it's practically impossible to find some other message with the same hash of X, it may be practically possible to find any pair of messages. So providing this property in hash functions is harder than providing the weak collision resistant property. If your hash function has the strong collision resistant property, in fact it also has the weak collision resistant property. But some hash functions have weak collision resistance but not strong collision resistance. Any questions before we compare the amount of effort required to break them? So try and distinguish between weak and strong collision resistance. You don't have to understand the mathematics of the birthday paradox, just be able to compare them. Understand, if you're the attacker, which one's easier for you to attack? Let's go to, and still on this topic, which properties do we need? Well, it depends on what we use a hash function for. So there are different hash functions available. We mentioned, I think, one or two last week. MD5 is one, SHA, the secure hash algorithm, is another hash function. What properties should a hash function have of those three that we've listed? Of these three, pre-image, second pre-image, collision resistance, or one-way, weak collision, strong collision resistant. It depends on what you're using the hash function for. Here are some examples. And we'll not go into the details. If you're using a hash and providing some digital signature, trying to confirm that this message came from a user, then it should have all three properties. If you're using hash functions for detecting viruses, so not about encryption but about detecting a virus, then it turns out that usually you just need the second property, weak collision resistance. A hash function that has this property is sufficient. It doesn't even have to be one-way property. You've seen hash functions in PHP, and you can apply the hash function on a password to store it in a database, for example. And we'll cover that in another topic. So when we take a hash of a password, the collision resistance is not such an issue. It's mainly about having the one-way property, or pre-image resistance. That's the desired property for password storage. So it depends upon what you use your hash function for as to what properties are needed for security. How do we break hash functions? Well, a brute force attack. And the one-way property and weak collision resistance, also called pre-image and second pre-image properties, a brute force attack against them, the basic approach is you try all possible values of y. That is, you need to find some message that produces some given hash value. So a brute force attack is to try all possible message. Take some message M1, calculate the hash. Is it the hash value we're looking for? If not, try the next message. M2, calculate the hash. And is it the hash value we're looking for? And keep trying until we get it. So try all possible messages. It turns out that if you try messages randomly, the amount of attempts that you need to find a collision, to find the right hash value, is proportional to the length of the hash value. If we have an m-bit hash code, for example, the length of lowercase h here is m bits, then approximately 2 to the power of m attempts are needed until you find a collision or you find the hash value. So, going back, that's for both of these properties, a brute force attack. For example, weak collision resistance, what we're doing, we know some hash value, we know the hash of x, we need to find another message y which has the same hash value. So what we do is we choose some random message y, calculate the hash, does it match the hash of x? If not, try another random message y and keep trying. And on average you'd take 2 to the power of m attempts, where m is the length of the hash value. It's not dependent on the message length, it's dependent upon the hash length. So if our hash length is 128 bits, for example, MD5 is a hash function, it has a 128-bit hash value, then we need 2 to the power of 128 attempts, about equivalent to a 128-bit key in terms of the amount of effort needed to break that. That is the same number of attempts. But with the strong collision resistance property, it's easier. It's easier for the attacker to find any two messages with the same hash value. And the amount of effort required is approximately equal to 2 to the power of m on 2, half the hash length. In our case, if our example hash length is 128 bits, the amount of effort is 2 to the power of 64. Okay, much, much less. That is, if we're trying to break the strong collision resistance property and the hash length is 128 bits, a brute force attack would take about 2 to the power of 64 attempts. But if we're trying to break the one-way property or the weak collision resistance property, then a brute force attack will take about 2 to the power of 128 attempts. Much, much longer. So, if we want to provide, if we need a hash function for a digital signature and we want to provide all three properties, that means the hash length must be long enough that the number of attempts cannot be made in reasonable time. And 2 to the power of 64 attempts is nowadays considered possible to try. So generally we need larger hash lengths because 2 to the power of 64 is in theory possible to attempt. 2 to the power of 128 is not. So if we had a 256-bit hash value, it would take 2 to the power of 256 attempts on the first two properties and 2 to the power of 128 attempts on the third strong collision resistance property. That would be considered secure for a brute force attack. Now, for a password, storing a password, if we need a hash function, the main property we care about is the one-way property. We don't care about strong collision resistance, so having a 128-bit hash value is sufficient in that case, because the attack would still take 2 to the power of 128 attempts. We don't care if someone can break the strong collision resistance property in this case. It's not required for security. So it depends upon what the hash value is used for, the hash function. It's easier to do a brute force attempt against the strong collision resistance property than against the other two properties. That's a brute force attack. There may be other attacks that take advantage of the algorithm design. So brute force can be applied against any hash algorithm, but if you know the hash algorithm and you can find weaknesses in the algorithm, maybe you can provide some other more intelligent attacks. And there are some attacks possible in theory, but they're quite complex. And we're not going to look at individual hash algorithms nor different attacks. But generally, they're not much better than a brute force attack. For example, there's an attack on the 128-bit MD5, takes 2 to the power of 60 attempts. Well, that's less than 2 to the power of 64, but not much. Okay? So 16 times less is not much if we don't save much by cutting down. SHA, which has different variations, but we'll mention shortly, is one hash function, and generally the attacks against some variations of the secure hash function SHA are considered infeasible, not possible. So the security of hash functions is mainly measured upon the hash length. Let's finish with just 2 mentions of 2 common hash functions which are in use. MD5, the message digest algorithm developed by one of the guys who developed RSA, Ron Rivest. The hash length is 128 bits. It was, and in fact is still commonly used. You'll see it in different applications still use MD5, but it's considered weak. The hash length, and there's some attacks that make it possible to find collisions. So it's considered weak and not recommended for use anymore. But it's still, you'll still see it in use. You may see it when you download files from websites. For example, you download an ISO of a Linux operating system, then maybe also the website lists the hash value. Why? When you download the file, you want to make sure it's exactly the same as the one that was published by the person who created it. So they also publish the hash value. When you download the file, you calculate the hash value. If it's the same as the published one, then you're quite certain that the received file is the same as the one that they published. If the hash value is different, the MD5 value is different, then maybe the file didn't download correctly or someone has changed it and you shouldn't use it. So MD5 is still in use but not recommended. And the replacement algorithm, the one that the US National Institute of Standards and Technology, NIST, developed was the secure hash algorithm. In fact, it has different variants. SHA-0 or SHA-1, SHA-2 and so on. Some of them are listed here, and in fact it's not just SHA-1, and that depends or indicates the length of the hash value. SHA-1 had 160-bit hash value. It's called the message digest size in this table, but the output. MD5 128 bits, SHA-1 160 bits. Then there's SHA-224, 256, so you can have different length hash values using the similar algorithm, just different length outputs. And the rest is about the details of the algorithm, which we're not going to cover. SHA-1 is no longer recommended. SHA-2, or the ones with, say, 256-bit hash values are recommended and in use, widespread use. The same organisation also has been developing the newer version, SHA-3. And in fact, they had a competition that ran for 5 or 6 years. People submitted their algorithm, and I think in October last year, so 2 or 3 months ago, they selected one algorithm out of 60 or so different algorithms to become the new SHA-3. I don't recall what the hash length is of this new algorithm, but it's SHA-2 is still considered secure. It's just that they want to plan for the future, and they have another one. And there are others. Okay, so they're just 2 common ones, MD5 and SHA, and there are others as well. We're not going to go through how they work. Brings us to the end of what we're going to cover about cryptographic hash functions. We're going to still talk about authentication in the next topic. But before we move on, everyone's clear about collisions, collision resistance, and how to attack them, how secure the different properties are. That's the hardest part that people find in this topic. Strong and weak collision resistance confuse people. One way to think about the strong and weak collision resistance, if you have a hash function that provides the weak collision resistance property but not the strong collision resistance property, versus then maybe we could say that that hash function is weak. Another hash function which provides both weak collision resistance and strong collision resistance is stronger than the first hash algorithm. So one that provides strong collision resistance versus one that does not, the one that provides strong collision resistance is stronger than the other one. Okay? If we can provide the strong collision resistance property, we consider that a more secure algorithm because it's harder to provide that property.
Isn't it easier to break?
It's easier to attack. That's what. Now, when we say we provide that property says it's impossible to attack. So, if a hash function provides strong collision resistance, it means it's impossible for the attacker to break it. So, if it's possible for the attacker to break it, then that property is not provided. I think last week we showed some quick examples on the screen of calculating the hash. Before we move on, any questions?
You said it was impossible to break, right? Strong collision.
If we say if a hash function provides that property, if a function has the property of strong collision resistance, that property says it's practically impossible to break. That it's practically impossible to find a collision by selecting any pair of messages.
But you said it's easier to break than the...
So if a hash function, say we have a hash function, we need to check does it have the property or not. We've got two hash functions, then if it doesn't have the have that property, then it's easier to attack, to break to find a pair of messages that have a collision. But once it has that property, by definition, the property says it's impossible to break. If it doesn't have this property, well, let's say a hash function didn't have either of these properties, okay, weak or strong collision resistance. If a hash function did not have either of these properties, you were an attacker, what would you try? You would try just choosing any pairs of messages because you know that you'll find a collision first. So if you want to find a collision, try and choose any pair of messages. That will find a collision or more chance of finding a collision than given some message, find another message that causes a collision. But once, say we have some hash function that this property is true, it holds, that means an attacker will not be able to find a collision. It would take too much effort. Think about those try and get your head around them. We may come back to them after our break if you have further questions. Confusing, isn't it? Okay, pre-image. Pre-image is the... Let's go back to our slide. Where do we say... What is the pre-image? The pre-image is the original message. That's just the terminology we use. So the pre-image of H is the message X, the message that produced that hash value. So X is the pre-image of H. H is the hash value. X is the message. Pre-image resistant means that given H, it's impossible to find the pre-image. Okay? Given a hash value H, the message X is called the pre-image of H. The property called pre-image resistant, or the one-way property, is this property that given H, it should be impossible to find its pre-image. It should be impossible to find the message that produced H. That's the pre-image resistant property. Or if we think of it in the term of normal hash functions, the one-way property. Our hash function should go one way, but going from the hash value back to the message should be impossible. The second property, this weak collision resistance, is about finding collisions. Okay? That's why we call it a collision resistant property. If this property is true, if it holds, then our hash function is resistant against collisions. It's impossible to find collisions. And it's the same with the third property. If this property holds, then our hash function is resistant against collisions. It's impossible to find collisions, but certain types, we distinguish between them. In the first one, as we said, given X, impossible to find some other Y that produces the same hash value. It's impossible to find that collision if that property holds. And the second one, given you get to choose any pair of messages. It should be impossible to find a collision if you can choose from any pair of messages. Does that answer your question about pre-image? So pre-image is just meaning the message that produced the hash value. I see people are still, brains are working. That's okay. Again? The second pre-image resistant is just another name for weak collision resistant. Okay, so just two different names for the same property. If a hash function, if we say it has this property of second pre-image resistant or weak collision resistant, it doesn't necessarily mean pre-image resistant. I think if you look in, I don't have it, but there's a picture in the textbook that shows that hash functions do not have to have all of these properties. A hash function that is strong collision resistant is weak collision resistant. A hash function that is weak collision resistant isn't necessarily strong collision resistant. and isn't necessarily one-way property.
So having strong collision resistance will have the weak collision resistance.
Yes. Yes, if it has strong collision resistance, it turns out it also means it's weak collision resistant. Yes.
I was going to ask, in what cases are strong collision resistance better than weak collision resistance?
In what cases are strong collision resistant better than weak collision resistant? When, or maybe the question, when do we need strong collision resistance? That may come out here, and it gives us the second column here, second pre-image resistant is weak collision resistant, and this is strong collision resistance. So weak collision, for a digital signature, weak collision resistance is necessary because it should be hard for the attacker to find some other hash value which is the same, or it's another message which gives us the hash value which is the same as the sent message. And the note says down here, we also like the strong collision resistance property if it's possible for the attacker to choose the original message. Let's go back to the digital signature diagram. Look at the top diagram. Remember, with a digital signature, what we do, we take a message, we take the hash of the message, encrypt that with the private key of the sender, that is, they're signing it, and send the message and that encrypted hash across the network. And what the receiver does is they check. So they verify the signature by taking the message and a hash of that message, same hash function, and decrypting the signed part using the public key of the sender. And if they match, they trust the message. They have verified the signature. If they don't match, something's gone wrong. Now, what can an attacker do? What the attacker may want to do is, let's see what happens if we have different properties. We have sent the message concatenated with the encryption using the private key of A of the hash of that message. That's what's sent across the network. That's in the middle part here. Let's say the attacker intercepts that and they want to modify the message, but they want to get the receiver to think that it's still signed by the original user. They want to fool the receiver. So what if they modify the message? They intercept and then send M prime, and they don't modify the signature, the rest. They send M prime and E PR of A hash of M. So all they do is change M, the sent message, to M prime, their own message. What does the receiver do? Well, the receiver takes the hash of the received message, M prime, decrypts this part, and they get the hash of M, and they compare it against the hash of M prime. And if we have our weak collision resistance property in our hash function, they should not match, because it should be, if our hash function is weak collision resistance, it should be impossible for the attacker to find another message M prime that produces the same hash value of the hash of M. So if our hash function is weak collision resistant, that means the attacker cannot find another message where the hash of that other message equals the hash of the original message. The attacker has M. Their challenge is to find another message m prime which produces the same hash value as m. If they can, this scheme would fail. Because if the hash of m prime does equal the hash of m, the receiver would try to verify the signature and everything would be okay, because the hash of m prime, they get that here, they decrypt the signature and they get the hash of m, they compare the hash of m prime and the hash of m, and they would be the same if we didn't have the weak collision resistance property. So that's why we need the weak collision resistance property for our digital signature. If we didn't have it, the attacker could modify the message. No, the attacker could find a message with the same hash value as the original and simply modify it, not have to modify this part, just modify the message, and the receiver would be fooled into thinking that it was signed by user A. So we do need weak collision resistance property for digital signatures. Do we need strong collision resistance? Well, remember, weak collision resistance, given m, try and find another m with the same hash value. Strong collision resistance, the attacker gets to choose m and m prime, any two messages. When does that happen? That would happen if somehow the attacker could get the sender to send a message that the attacker chose. If the attacker chose M and user A signed it and sent it, then the attacker needs to find some other M prime, with the same hash value, which is this attack against the strong collision resistance property. That is, if the attacker can choose the original M and also choose M prime, then that's this challenge of you get to choose any two messages and try and find a collision. Choose two messages which produce a collision. That's easier for the attacker. So if the attacker can choose this message, then for this to be secure, the property of the hash function should be that it is strong collision resistance. If the hash function is not strong collision resistance, and the attacker can choose the original message, and of course they can also find another message with the same hash value, then they will fool the receiver into thinking that the message came from A when it came from someone else. In some cases, the attacker may be able to choose the original message. In some cases, they may not. It's in the slides, it's a chosen message attack. The attacker somehow gets to choose the message that was sent. That's, for example, you're the attacker. I'm sending a message to the director about changing grades of students. I choose the message normally and I sign it. So I choose M and I sign it with my private key and send it. Well, if somehow you can get me to if you can get me to send a message of your choosing, so somehow you have a message and I sign it using my private key and send it, then that's a case where you as the attacker got to choose the message. And there are some special cases when that may occur. It's not so common, but in some cases it will occur, where the attacker can control what the sender is sending as the message. So in some cases we need strong collision resistance. Some cases for digital signatures we just need weak collision resistance. We definitely need weak collision resistance. I think the textbook, and it's a bit more detailed than what we have time to go for, but there's a good example in the textbook of how does a user in practice get someone to generate a message M and then make it easy for that attacker to find some other message and hence break such a signature scheme. There's an example of how to generate many possible messages by many 2 to the power of 60 or so different messages. And it's not so hard, in fact, that the attacker If they can get the user to create a certain message, they can find another message with the same hash value. It is possible in some conditions. Okay, any further questions about hash functions? What have we got in the last 10 minutes? Before we start the next topic, which is still on authentication, let's look at one example of something different. Rather than starting, let's look at an example of some of our algorithms we've mentioned so far in use. This is a Wireshark capture from secure web access. So I'll only show a few packets here, but what I did in this case, I accessed a website using HTTPS. Okay, you've used it in a number of cases when you access a bank or some secure login in some cases. In fact, when you log into Moodle for the quiz, that login page requires you to use HTTPS. And we'll mention that in another lecture, but it basically is using HTTP on top of some secure transport protocol so that the data that you send between you and the web server is encrypted. Let's scroll down and find some packets. This is when we start. The green ones above were using normal HTTP. This is the case using real HTTPS. We set up a TCP connection, SYN, ACK, and then before we send the request to the web server, so you know with HTTP you send a GET request to the web server sends a response. With HTTPS, before we do that, we set up a secure connection between your client, your browser, and the web server. And the protocol for doing that is called TLS, Transport Layer Security. Client sends a hello message, and inside that hello message is many details, but one of them that we see, the client informs the server what algorithms it supports. So this is just setting up. So what we need to do is, when I connect to the web server, we need to be able to encrypt our traffic. Encrypt, sign data, use hash functions. So what algorithms do we use? So these hello messages are just for the client and server to inform each other what algorithms they support, and they'll choose one. And the cipher suite's here. So this is the client saying, I support these different combinations. And you don't have to remember all of them, but TLS is the name of the protocol. And then we see the way to read it in this selected one. Let's go from the back. It's easier. This is the hash algorithm that's going to be used. So when we sign things, when we perform authentication, we need a hash algorithm. What hash algorithm? In this case, SHA is the hash algorithm. That's what the client offers to use, SHA. We're going to encrypt data with symmetric key cryptography. When we encrypt our data, normally for sending to the web server and the web server sending back, we use symmetric key cryptography because that's faster than public key cryptography. What algorithm? AES, 256-bit key, and CBC is the mode of operation. So that's what the client offers for data encryption. And then there's two other parts, and these two. There's the way to exchange a key, to exchange a secret. Before we can encrypt data, both the client and the server need to know some secret. because to encrypt data with AES, we need a secret key. What is that secret key? Well, we can use an algorithm to exchange a secret. In this case, there's a variation of the Diffie-Hellman secret key exchange algorithm. It's called elliptic curve cryptography Diffie-Hellman exchange. So we would use Diffie-Hellman, a variation of Diffie-Hellman, to exchange a secret between client and server. To sign any data, we would use DSA. DSA is an alternative to RSA for signing information. So, as we've seen, we sign with some private key. Well, DSA, just a different algorithm than RSA. So, we select an algorithm for exchanging a key, exchanging a secret, for signing and authentication, for data encryption, the mode of operation, and the hash algorithm. So normally we need algorithms for all of them. So
Hash and signing generally the same.
signing uses a hash algorithm. Signing can use, here we used an encryption operation here. What algorithm? In this case, we'd use DSA here. We also used a hash function. What algorithm? SHA in this case. And in fact, the client supports many different sets of algorithms. RC4 is supported. Camellia is an alternative to AES. Diffie-Hellman, instead of the elliptic curve, Diffie-Hellman, just plain Diffie-Hellman. RSA instead of DSA. So different algorithms are supported by my Firefox browser. And the server sends back a reply, server hello, and in there it contains, where is it? It contains what it selects. So the client says, I support all these algorithms, the server chooses one based on what the server supports and what the client supports. And in this case, the web server chose this one. SHA is the hash algorithm. AES, 256-bit key with cipher block chaining is the mode of operation and the symmetric key encryption. And in this case, it uses RSA. And it uses RSA for the secret key generation and also for the signing. So it uses the same algorithm for both operations there. So that's just an example that in practice, for network communications, we make use of all of these algorithms. Symmetric key encryption, public key encryption for signing, for authentication, hash functions, modes of operation. And then there's a few more messages to exchange. Then eventually we start sending data and it's encrypted. You know, when you capture HTTP, you can see in Wireshark the GET requests. If you look in these packets, you will not see the GET requests. You'll just see random looking characters because it's encrypted. So we set up the encryption and then we start encrypting the messages using AES in this case. We may show another example capture at a later stage and return to the details of the protocol in a different topic. Let's stop there and for those that haven't collected their quiz,